In this lecture, we are going to discuss about a transient and a steady state response. So let's see what we are going to cover in this lecture. First, we discuss about what do we mean by time response analysis. Then we'll discuss about transient and steady state response. And at the end, we are going to discuss about time response specifications. So let's start. We'll start with time response analysis. So time response analysis, or it is also called as a time domain analysis of a control system, is where we study variation of the output with respect to time. So here we will be having system, and to that system we are going to give input, and we'll see how the output of the system changes or varies with respect to time. Let's take this fan as an example. We know that in fan we can regulate or we can control the speed of this fan with the help of a regulator, which will be having certain position mark on it. So let's say this is 0, we are having 1, 2 and 3. So it will be having, like, if regulatory changes from 0 to 1, one will be having certain RPM or certain speed associated with it. Say here we'll consider that it is 100 RPM. Similarly, when it is going to 2, say it is 200 RPM, and so on. So now when we changes, and of course it need to be switched on. So when we are changing from 0 to 1, we expect it to have 100 RPM. When we are providing input to it and it is set to 1, we are expecting it to achieve 100 RPM. So how it is going to achieve that 100 RPM with respect to time? If we are monitoring that, then it will be considered as a time response analysis of the system. So here we are providing input to the system and we are monitoring its output. Now whenever we say that system is performing satisfactorily, so in that case the output of the system with respect to time must be within certain specified limit. So this is a limit on this system. So if we are changing from 0 to 1, and if it is going beyond this limit or it is falling below this limit, then in that case we can say that system is not performing satisfactorily. So the speed of this system or this fan need to be around 100 RPM. That is what we have designed for. So whenever we are doing this kind of a time response analysis, and with respect to it we will be getting different results. So based on those results we can tell about the stability of the system, whether the system is stable or it is unstable, and also we can get the accuracy of the system, or how accurate that system is to achieve the desired output. And in this way we can completely evaluate the entire system for its performance. So whenever we talk about the time response analysis of any system, or whenever we do this kind of time response analysis, we provide input to the system and we monitor its output with respect to time. So generally we find these two type of response in the system. One is called as a transient response and second one is called as a steady state response. Whenever we do the time response analysis, we plot the output with respect to time. So here this graph shows system behavior when we are providing certain input and we are measuring its output here on y-axis, and time is given on x-axis. So we can see that in initial phase system is behaving abruptly. So this is a phase when system is behaving in a oscillatory manner, or when system is not acquiring the desired output. Say the desired output is here. This is the line, or this is the point where we are expecting the output. So system initially it is oscillating, and later on we can see that it is stabilizing near the desired point. So whenever we are having a fluctuation from starting, that range or that interval is called as a transient phase. So here this phase we are going to say as it is a transient phase. And later on the system will going to stabilize near the desired value or near the desired output. So that phase is called as a steady state phase. So this state or this phase on the right hand side is called as a steady state phase, where system is going to have a stable value of the output. So we can have this kind of behavior with any kind of system, like if we consider a car, when you switch on the car and start it, so you can feel the vibration in initial phase. As soon as we start the system or we start the car, we feel some vibration, and later on engine RPM will stabilize. So the phase when we are starting or when we are giving an input to this car, the engine will going to vibrate, and that phase of vibration is called as a transient phase, because later on it will stabilize. And the generally transient trend or transient phase we are going to expect in a system, because when we provide input to the system, that input will try to overcome the resistance or inertia force or maybe frictional force that is there in the system. It need to overcome that, and during that phase it behaves abruptly that we don't generally desire, and that phase is called as a transient phase. And later on the system will stabilize, and that stable phase is called as a steady state. Same happen with fan also. If we set a regulator to some speed and we switch on fan, it start with a noise. So that noise occur because the input is trying to overcome the inertia and frictional force that we are having in the system. During that initial phase it will going to behave that we don't expect it to behave, but that is a portion we cannot eliminate, or that is a phenomena we cannot eliminate. So that phase is a transient phase, and later on it will going to stabilize and behave in a normal way. So that phase, when it is behaving normally as we expected, so that phase is a steady state. So whenever we talk about the total response of the system, it will be always addition of both transient response as well as steady state response. So we will be having both these elements if we consider any of the system. Now let's discuss about the transient and steady state response. So about transient, as we have discussed, so this is the part of total response that occur in initial phase of any system when we are going to give it an input. Or we can define this transient response in another way, like we can say that it is the part of a response which goes to zero after a large interval of time. So we can consider same response curve here. So this is a phase when a system is going to behave abruptly or in an uncertain way that we don't expect it to behave. So that portion is called as a transient phase. And we can see that after some interval of time, say like here at t, it will vanishes, it will go to zero, and we will be having a steady state response here. So in this way we can define the portion of total response which goes to zero after some interval of time. So from transient response we can extract various information about the system, like the time interval after which the system is going to respond. So here we know that when we are going to provide input to any system, we expect that it will going to give us a certain output. But when we give input to the system, directly we are not going to get a, or instantly we are not going to get output, because this input will be requiring some time in order to go through the system and to overcome frictional force and other resistive force that system will have, and later on it will going to give us the output. So it may happen that we will be having certain lag between input and output. So that time we can determine in a transient response. So we are going to give input to the system, and as soon as we are able to see the output, so what is the time difference between the input when we are applying it and we are getting output, so that time difference we can know. Now the next thing that we can determine from the transient response is the time taken to achieve the output for the first time. So here, if we see the graph, we are having set the output, the desired output is set at here. This is the expected output that we want from the system. So how much time this system is taking to give us the output first time. So this is the first time. So here we can see that this is the time that the system is going to take in order to give the output first time. So this parameter we can determine from a transient response. Similarly, we can determine whether or not the output shoots beyond the desired value and how much. So from the transient response, we can see that how system is going to achieve the output and whether it is going to shoot above the outputs. Like here, we can see that it is going beyond the desired value. So how much it is going beyond the desired value, that also we can extract from the transient response curve. Now next thing that we can extract from the transient response is whether or not the output oscillate about its final value. So it may happen that when we are going to give input to the system, its output may oscillate about the required value, and later on it may stabilize, like here we can see in this graph. Or it may happen that when we are going to provide input to the system, it just gradually go and achieve the desired output in this way. So these things we can extract or we can say from the transient response information. Now next thing we can have is the time that it takes to settle to the final values. So this information also we can extract from the transient response, how much time that system is taking to stabilize to the required output. Or we can, in other way, we can say that how much time the transient response is taking to dry out. So in this way, we can get the settling time of any system. Now let's discuss about the steady state response. So we know that in a steady state response, system already stabilized to the required output. So in other way, we can say that it is the part of response that remains even after the transient have dried out. So this portion of the response will remain unless and until we switch off the system. Now let's see what we can determine from a steady state response. So we can find the time that output take to reach the steady state. So from the steady state response portion, we can determine how much time the system has taken to reach steady state. So from this response curve, or from this response, we can determine. So from this response, we can determine how much time the output has taken to reach to the steady state value. Similarly, we can determine whether or not any error exists between the desired and actual value. It may happen that if the output, like in case of RPM that we discussed for fan, say it is 100 RPM. So if the output achieved in a steady state is 100, so here we can say that there is no error. But if the RPM here that is achieved by system is 99 or maybe 101 RPM, so in both the case we can say that system is having error. So in this way we can extract this information whether there exists any error or not from the steady state response. Now whether this error is constant or it is zero or it is infinite, this also we can extract from the steady state response. So if it is constant and it is within the limit, or the error is zero, so in both the case we can say that system is stable. If we are having an error which is moving towards infinity, so that is a case when we are having system which is unstable. Now let's discuss about the time response specification. So about any system, we know that the response will be divided into two parts. One is transient and one is steady state. So mostly the problem that system faces is in a transient phase, because in that phase system is going to behave abruptly. That is a phase that we don't want, but we cannot eliminate that also. So what we can do, we can control that phase by defining some parameters. So the parameter that define that phase of a transient response is called as time response specification. So whenever we are designing any system, we need to decide about these parameter that is acceptable to us. Now after design, we will be checking that system. So if all these parameter are within the limit, then that system is going to behave according to our need. But if any of these parameter goes beyond, so it will be having an adverse effect on the system's performance. So these parameter that will going to define how the system is going to behave, so we need to study them carefully and decide about them carefully. So here we are having a number of parameters, so we'll go one by one. So what we are going to do, we are going to define them and we'll discuss with respect to this graph. So let's define the first term here. The first term is a delay time and it is represented by TD. It is the time needed for the response to reach half or 50% value of the very first response. So here we can see that whenever we are going to give input to the system, it will start, the output will show up from 0 and it will rise to some value. So how much time it is going to reach to half of this one value, because one is the desired output that we are expecting from the system, and this is the first response that we are getting when we are providing input to the system. So how much time this response is taking to reach 50% or half of this expected value, so that is defined by TD. So we can see here this Uh, so on this graph, we are having TD here. So this is the time, or TD is the time required for the output to reach half of its final value. Next is a rise time, is represented by TR. So it is the time required for the response to rise from 10% to 90%, or from 5% to 95%, or from 0 to 100% of its final value. So TR, we can see on this graph, is this value for this example. The response is going from 0 to 100%. Okay, so for this case it is going from 0 to 100%. So that way we are defining TR here. So it is the time required for the response to rise from 0 to 100% for this case. So based on the nature of the system, we will be having ways of defining this rise time. For example, for underdamped system, where we are having zeta value, that is a damping ratio, is less than 1, so that is called as a underdamped system. So for underdamped system, rise time is considered from 0% to 100% of the required response. For overdamped system, when we are having zeta greater than 1, so for that system, we will be having a rise time defined as 10% to 90% of the required value or required output. Similarly, for critical damping system, that is when we are having zeta is equal to 1. So for that case, we define rise time as 5% to 95% of the output. Next time specification is peak time, that is defined by TP. So it is the time required for the response to reach the first peak of the overshoot. So here we can see on this graph, this time TP is here when our system is moving from 0 to the highest peak. So this is the overshoot that is occurring when response is going above the desired value. So here we can see that from 0 to the maximum value, and that maximum value is going beyond the desired value. So how much time it is taking, so that time is defined by peak time. So in another word, we can say that peak time is the time required for the response to go to the overshoot. Next is maximum percentage overshoot. So it is the maximum peak value of the response curve measured from C infinity. C infinity is what? Is this value, the desired value. We expect that at C infinity, or the output at infinity, is the desired output that we are expecting. So for this case, we can consider this to be 1. So beyond 1, how much the response has gone up, so that value is called as the maximum overshoot, and that generally occur with the first response of the output. So if C infinity is equal to 1, or we can say that the output is equal to the desired output, so in that case we can directly say that maximum percentage overshoot is this MP value, that is how much the output goes beyond the desired output. But it may happen that the output may not reach to the desired output because of various reasons. So for that we may have certain range in which it will be. So if we are having that case when the output is not equal to the desired output, so in that case we define the maximum percentage overshoot with this formula, that is CTP, that is the output at peak time minus the output at time infinity divided by the output at infinity into 100. So we will be using this formula to get the maximum percentage overshoot. So first formula we will be using, or first case we will be using, when the output is equal to the expected output, and second we are going to use when output is not equal to the expected output but it is under a certain limit. Next time specification is settling time, that is defined by TS. So it is the time required for the response curve to reach and stay within 2% to 5% of its final value. In simple term, we can say that time required for the system to stabilize or to settle down to the required output. So that time is called as a settling time. But as we know that exactly achieving the required output is not always possible, so we put certain limit to the output. So if output is within that limit, then also we can consider that is in a stable state or steady state. Then last time specification is steady state error, that is represented as ESS. It indicates the error between actual output and the desired output as time tends to infinity. So steady state error give us the difference between the actual output and the desired output, and this we measure when time tends to infinity. Now let's revise what we have studied. So we started with a time response analysis. Then we discuss about these transient and steady state response. And then at the end, we discuss the time response specifications. So with this, we'll end here.